All right, do you remember that one? How can we define what a limit is? Very casually. Okay.
It's for like a line.
We can say that a limit is the y value a function approaches. All right, so there's our word, approaches. Bless you. From the left and right of an x value. Kind of outside the box, that's fine. So this is how we can define a limit. It's not the most formal definition, but it's the one that makes sense to us. So today we're done with the graphing portion of it. We're gonna actually use some algebra to find a limit. All right, there's 3 ways that we can find a limit algebraically. The first one being you're just gonna plug it in. We call it direct substitution. All right, direct substitution just means you literally plug in the number into the function. All right, that's always what you're going to try first, is direct substitution. All right, the next thing, let's say you plug something in right away and you get something strange. You cannot just say the limit doesn't exist. The most common way that the most common problem that you guys are going to run into when just plugging in the value in direct substitution is you're going to get a 0 over 0, maybe. All right, so you're most times going to get a 0 over 0 when you're plugging in in direct substitution and you see that it doesn't work. This does not mean that the limit does not exist. Chances are, if there's a 0 over 0, it means there's maybe a hole, and it actually does approach something, but a lot of times it does not mean that the limit does not exist. There's actually a lot of work that goes into saying a limit doesn't exist. The next thing that you would do if direct substitution doesn't work, you run into a strange problem like a 0 over 0, is you would simplify first, and then you would do direct substitution. Right, the most common ways that we would simplify is just what you did in your warm-up, is you can factor and cancel. Factor and cancel. Or you rationalize if there's a radical. All right, those are the most common ways that you would simplify. After doing this, you should be able to just directly plug it in, and then you'll get an answer. The third way, which we're not going to touch for a little bit of time, we might revisit this in a few months after we learn more about derivatives. But the third way, you don't have to know it right now, but I'll just write it down, is something called L'Hopital's rule. This is specifically for if you get a 0 over 0, or when we get to infinities, infinity over infinity. All right, but for today, what we're going to focus on is this. You don't really have to worry about this one right now. We're going to get there in a few units. All right, so we're going to start with direct substitution. Let me zoom out so you guys can see. We're going to start with direct substitution. Direct substitution literally just means you're going to plug in the value. So again, let's kind of revisit some notation. How would you read number 1? Okay, so we're going to solve this limit. With direct substitution, right, this number, you should be able to just plug it in everywhere that you see an x, and you should just get an answer right away. All right, so when you do this, it's going to get you negative 1 squared plus 2 times negative 1 minus 4. Super easy, right? We can just directly plug it in. And that's going to get us 1 minus 2 minus 4, so negative 5. Our limit here is negative 5, which, if you think about it, makes sense. What shape does this make? Let's say we were to graph it. We're not going to do a ton of graphing today, but if you were to graph this, what shape would it make? Okay, a parabola, right? It would be an upward-facing parabola. It would look something like this. What we're saying is that at negative 1, I don't know where this is, right? But let's just say it looks something like that. At negative 1, we're going to have a y value of negative 5. And if you know what a parabola looks like, I mean, it's pretty obvious, right? At negative 1, if you know that it's approaching that value, that's what it would look like. So yeah, this one, again, just direct substitution. This is the limit as x approaches 2 of this function, the square root of 3x minus 2. With direct substitution, the next step, all you have to do is just plug it in. 3 times 2 minus 2 under square root, then you get 6 minus 2 under square root, which is square root of 4, which is 2. All right. Now let's say you tried doing that with the next one. All right, I know it says factor and cancel, but let's say we didn't see that and we want to try plugging it in. If we were to just plug this in using direct substitution, we would get 4 times 0 squared minus 5 times 0. Over 0, what does that get you? Good, it gets you a 0 over 0. Now, you guys, when plugging in, might run into a lot of 0 over 0s. That doesn't mean the limit doesn't exist. A lot of times it does exist, right? So the next best thing that you would do is try to simplify a little bit more. How do we simplify this function right here? Okay, good. We can take out an x. All right, I'm still going to write the limit, right? So that's another thing, is that as you guys are working through these problems, you guys might like to shorthand some things. Until we do the direct substitution, like how we did here, you can't just ignore this limit right here. If you haven't done anything with it, it still needs to be there. On your tests and quizzes, I'm going to follow through on your work. Right, so we didn't plug in anything yet. Keep the limit notation there. It's the limit as x approaches 0 of x times 4x minus 5 over x. All right, and then we can see that this cancels, x and x. We're still not plugging in, so I'm still going to write the limit as x approaches 0 of 4x minus 5. We got rid of the fraction completely, so now what can we do? Just plug in 0, right? And now that we're directly substituting, we don't have to write the limit notation anymore. This is the same as just 4 times 0 minus 5, so negative 5. All right, are we all okay with that? Nice. All right, same exact thing with number 4. This is the limit as x approaches negative 7. When you plug in negative 7, you can clearly see on the bottom it's going to give you a 0. On the top, when you plug it in, it's going to get you a 0 as well. So what do you think we need to do here? Okay, good. We can factor the top, and then we can cancel. How does the top factor? So we get the limit as x approaches negative 7. Right, the bottom is x plus 7. You got, what? I'm sorry, x plus? Okay, yes, x plus 7. And then what's the next one? 2x minus 1. Okay, guys, yeah. We can't forget how to factor. What do you guys do? The little slide and divide thing that you learned from Mrs. Meadows, maybe? Okay. So we should get something like this. You can also do it by grouping. I personally, this is very unpopular, I personally just like to guess and check. So if I see an x plus 7 on the bottom, what factor do we think should be on top? Also an x plus 7. If you're doing x plus 7 times something, what's the only thing that you can multiply x by to get a 2x squared? A 2x. What's the only thing that we can multiply a 7 by to get a negative 7? A negative 1, right? And then you can always double check it if you need to. But I personally like to guess. alleviates some mistakes here and there. All right, but then you get something like this, and then you can just go ahead and cancel these out. And then you end up with the limit as x approaches -7 of 2x minus 1. What can we do here? Just plug it in, right? Now this looks pretty normal. We can just plug it in right away. So this is going to be 2 times -7 minus 1, which gets you what? Nice, -15. Right, so what does canceling tell you about the graph? What can you expect at whatever makes this 0? A hole, right? Okay, so now let's try something like this. All right. Looks a little bit different with the radical and the fraction together. If you plug in 5 right away, this is another one that's going to get you a 0 over 0. Now, anytime there's a radical and you get a 0 over 0 after plugging it in, you're always going to rationalize wherever, no matter where the radical is. So typically we say that radicals are unsimplified when they're on the bottom. If it's on the top, doesn't really matter. We're going to try to rationalize it anyway to see if that helps us a bit. So we're going to do the same thing as we always do in rationalizing, is we're going to multiply by the conjugate. What's the conjugate of this on top? X plus 4, what? Plus 3. And we're going to do that to the top and the bottom. All right. And then so we end up with the limit as x approaches 5 of, can we simplify the top? What's our little shortcut? What's the first thing that we're going to write? First times the first, what does that get you? Just x plus 4, right? The radical goes away. There's a minus and a plus, so this is going to get us minus. Last times the last is 9. Over, let's not do anything with the bottom, right? It already looks kind of complicated as is. Let's see if we can get away without doing anything with it. So it's just going to be x minus 5, the square root of x plus 4 plus 3. All right, what can we simplify here? Good, right? The top becomes x minus 5, so this becomes the limit as x approaches 5 of x minus 5 over the bottom stays the same. All right, and then you can see that the x minus 5 cancels. All right, you guys agree? Nice. So we can cancel these out. Again, you still need to write that limit notation. We haven't plugged anything in yet. So this is going to be the limit as x approaches 5 of 1 over the square root of x plus 4 plus 3. What can we do now? Now we can plug it in, right? After we fully simplified it, we can plug in. And now that we're plugging in, we don't need this limit notation anymore. It's just going to be 1 over 5 plus 4 under a radical plus 3. 5 plus 4 is 9, square root of 9 is 3, and 3 plus 3 is 6. So we get 1 over 6. Okay, so definitely more algebra heavy today versus yesterday. Good, right? Because this limit is the limit as h approaches 0. So we don't really care about the x right now. But what do you notice if you plug in h right now, what happens? It's going to get you a 0 on the bottom, right? And we can't have that. So what we're going to do is we're going to try to simplify this as much as we can. And we're just going to hope that something cancels out. And you guys are going to learn in a few weeks that something like this, there's always going to be an h that cancels out. All right, so let's go ahead and simplify. Let's do x plus h squared. Let me write the little limit, the limit as h approaches 0. X plus h squared. We should be able to do that quickly. What does that get you? Okay, so we get x squared plus 2xh plus h squared. There's a rule for squaring a binomial. If you remember it, it should make it quicker. If you need to FOIL it, write it twice and FOIL it, then you should do that if you need to. Now this negative 3 we can distribute, right? And this is just going to get you a negative 3x minus 3h. And then this negative right here we can distribute. It's going to be negative x squared plus 3x. And this is all going to be over h. All right, why did we do that? It looks a little bit more complicated now, right? Because what happens on top? Okay, good. So things that are like terms we can combine, right? What are like terms here? Good. The x squared, what happens with the x squareds? Good. Cancel out. What else cancels out? The 3x's. Good. So then what are we left with on top? 2xh. Good. Plus h squared minus 3h over h. Nice. How does that help us? What can we do now? Good. We can take out an h on top and then cancel it out, right? We see that this has an h, this has an h, and this has an h. So if we factor out an h and cancel it out, we're left with 2x plus h minus 3. What can we do now? Just plug in 0 for h, right? So then now that we're substituting, we don't need the limit notation anymore. This is just 2x plus 0 minus 3, which very simply is just 2x minus 3. Say that again? Yeah, so this is our final answer. I know it's not like a nice number as we usually get. Not always is it going to be like that. If you have two variables, only the variable that's in this limit right here should go away. But the other variable is still going to be there. That's perfectly fine. Let me zoom out. Okay, do you remember piecewise functions? Maybe a little bit, right? Hopefully a little bit. Yeah, these definitely look a lot scarier than they actually are, right? If you remember anything about piecewise functions, very rarely are you doing anything with all the functions that you see. It's called a piecewise function because it's broken in pieces. You're only going to work with one at a time. But let me give you an example of a pretty basic piecewise function, right? Pretty much yesterday when we were doing limits with the graph, all we did were regular piecewise functions with the graph. So let's say I give you, I don't know, something like that. What kind of shape does that look like? It looks like half a parabola, right? So let's say this particular piecewise function, I have half of a parabola. And then let's say right here, I'm going to have an open circle, and then it's just going to be a line going down. Right? If I asked you to find limits with this graph, right, we could do that pretty easily. The only difference here is that we're doing it algebraically. Now, what you guys need to understand is exactly what we were doing yesterday. When you're looking at this particular spot where things are a little different on the left and on the right, that matters when we're dealing with piecewise functions as well. So when you look at this particular piecewise function, the part where things are changing is where x is 5, or negative 5, sorry. All right, so where x is negative 5, we know that something is going to be different on the left versus on the right. X is less than negative 5. What side of the graph is that? Is that the left or the right? So we know that if we're looking for a left-hand limit, we know that we're looking at this function right here. X is greater than or equal to negative 5. What side of the graph is that? The right-hand side. Right, this is the right-hand side. So now we can very easily answer these questions, 7, 8, and 9. If I'm looking for the limit as x approaches negative 5, this means from the left. Right? Which function am I going to want to plug into? The top one, because that one is the one that we're approaching from the left. Even though this is a less than or equals, right? Just like yesterday with the open circles, guys, you don't have to worry about the less than or equals. As long as it's approaching that value, that's all we care about. So let's just directly plug it in. We can direct substitution this, right? minus negative 5 is going to be plus 5. So we get the square root of 16, which is 4. Pretty straightforward. Are we okay with that? Okay. What about the next one? The limit as x approaches negative 5. This is from the right, so where am I plugging negative 5 into? The bottom one, right? I'm plugging it into this function right here. Right? It looks like a fraction, which it is, but that doesn't always mean you have to simplify and factor and cancel. A lot of times you can get away with just substituting. So let's try it. It's going to be negative 5 plus 3 over 5 minus negative 5 squared, which is going to get you negative 2 over 5 minus 25, which is negative 20. How does that simplify? 1/10. Okay, good. So we have a left-hand limit and a right-hand limit. These both exist. But let's say I want to take the limit as x approaches negative 5. Does that exist? No, right? Why doesn't it exist? Good. The left and the right are not the same. So we can just say the left doesn't equal the right. All right, similar story with this next one. Again, this is another one that looks like a little bit harder than it actually is. But it's just because there's 3 functions here. So let's look at this first one. We have x is less than negative 1. What does that mean? We're looking at this particular function from the left. All right? This next one, we're going to look at it piece by piece. What does negative 1 less than x mean? Just this portion. Where are we looking at it? Okay, which means what side of negative 1 is this function on? It's on the right. This one's on the right side. All right, and then we can look at this other part of it. X is less than or equal to e. What does that mean? It's on the left side of e. So I'm going to say this is left of e. And just to be a little bit more specific, I'm going to say this is left of negative 1, and this is right of negative 1. You're not going to write this every single time. I'm just writing it for now so that you guys understand visually where it would be on a graph. And then lastly, x is greater than e. What does that mean? This is on the right side of e. So on the right side of e. All right? All right, now if I were to just ask you the limit as x approaches negative 1, all right, there's 2 things happening at negative 1. So which 2 functions are we going to plug negative 1 into? Okay, we're going to plug it into the top and the middle. And this limit exists if the top and the middle, when we plug in negative 1, are what? Are equal. Good. I'm going to give you guys a second. How about you guys verify that? See if the top and middle, when you plug in negative 1, are equal. Okay, good. Yeah, so we always need to make sure the left equals the right. When you do, it looks like the top one's going to get you square root of 9, which is 3. The bottom one, we get 26 minus 5 over 7, 21 over 7, which is 3. So both sides equal 3, so that means this limit is 3. All right. Let's try the same thing. Well, not the same thing. Let's try 11 now. This is the limit as x approaches e from the right. So which function are you plugging e into? The bottom one. So we're going to do ln of e to the power of 3. Remember our properties of logs? What is this equal to? 3. All right, so this is equal to 3. What about just the limit as x approaches e? We know that the right-hand side is 3. What should we also look for on the left-hand side? What do we want that to be equal to? 3. We want it to be 3 as well, right? So let's plug it in to, I think you said the middle, right? So we're going to plug it into the middle equation, or function, since that one has the left side. Bless you. And let's see if that works. 26 minus 5e squared over 7. I mean, is there anything we can do with that? No, right? That's Definitely not 3, so does this limit exist? No, so this one I'm going to write D and E does not exist. All right, the left doesn't equal the right.
Wait, so for number 11.
So special trig limits, you have to memorize. So I'm going to say memorize. The best way to understand these is by looking at the graphs of these functions. I might open Desmos again, but these are just special limits that you don't have to really show any work for. If you see these, then you can just answer them right away. So as x approaches 0 the limit as x approaches 0 of sine x over x, that's always going to equal 1. Same exact thing if it was the reverse. If it was x over sine of x, these both equal 1. All right, the limit as x approaches 0 of 1 minus cosine over x is going to get you 0. Same exact thing if I flip it. That's also going to get you 0.
Do you know why? Is it just like the rule?
All right. So where you guys would apply these, right, I wouldn't make it as simple as you see it and you get an answer right away, right? This doesn't quite look like the rule that we just talked about, but it looks similar, right? What would have to happen for us to be able to apply the rule? I see a sine of 3x on the inside, so what should we want on the bottom?
3x.
Also a 3x, right? So it doesn't matter what's inside here, as long as what's inside of the sine function is the same on the bottom, then it's going to equal 1. How do we get a 3x on the bottom? What's missing? A 3, right? So if I multiply 3 here, that would get you exactly what you're looking for, but you can't just do that out of nowhere. What should you do to the top? Also multiply that one by 3. So essentially what we did was we did the limit as x approaches 0 of 3 times sine of 3x over 3x. And then we know that this limit as x approaches 0 is equal to 1. Now, one of our properties of limits is that if you have just a constant on the outside, that's the same as if you have the constant outside the entire limit. So I'll actually write that down. This is the same as 3 times the limit as x approaches 0 of sine of 3x over 3x. You can always do that if if there's a constant. You can't pull out a variable, but you can pull out a constant. All right, so now that we did that, we know that this whole thing is a special trig limit, and this equals 1, so this is the same as 3 times 1, which is just 3. All right, are you okay with that?
So you have to multiply.
No, right? We don't have a rule for tangent, but what's something that we can do to help us a little bit? Which is 1 over sine over cosine, right? So tangent is the same as sine over cosine. So let's write that down. This is the limit as x approaches 0 of sine of 4x over cosine of 4x, and this is all over 8x. All right, I don't really like the way that looks. How can we fix that? Okay, good. We can keep change flip, and then we can do times 1 over 8x. All right, so then this is going to get us the limit as x approaches 0 of sine of 4x over, I'm going to write the 8x in front so that I'm not confused with the cosine. 8x times cosine of 4x. It looks like we almost have a special trig limit with the sine of 4x, right? But that would work if this was not an 8x, but a 4x, right? Is there any way to make that 8x a 4x? if you divide it by 2, right? But you don't want that 2 to just disappear, right? So we have to be kind of creative. We have to think outside the box with our algebra here, right? So this is going to be the limit as x approaches 0. Sine of 4x we keep the same. This is the same as 2 times 4x. All right, do you guys agree? I didn't really change the value of it at all. I just split it up so that I can see the property. Times cosine of 4x. All right, just like with the constant multiplier, you're able to split limits up. All right, so we can see now that this sine of 4x over 4x is our special trig limit. I'm just going to do a little bit more algebra to try to get the special trig limit in one factor, and then in the other factor, everything else. All right, so let's make this the limit as x approaches 0 of sine of 4x over 4x. And then this is still the same limit. I'm just splitting it up so that it's easier to see, right? You don't really have to do this if you understand it. But just so that it's easier to see, do you see that I didn't change the actual function at all? I just split it up differently. We know that this limit is 1 times 1 over 2 times cosine. We can plug in now. Cosine of 0. Right, here is where I did my direct substitution. What is cosine of 0? Uh-oh. Do we know cosine of 0? So then this is the same as 1 times 1 over 2 times 1, which we can simplify to 1/2. Yeah, so I'll write that down. From here to here, I did direct substitution. I did a whole bunch of algebra first, but here I did direct substitution.
Wait, so how come you didn't substitute the 0 and the 2?
Okay, good question. Just because if you did, you would get the 0 over 0, but we can see that that's a property. The property is that it's equal to 1. The only reason we did it here is because this part is not a property, but this part was. So I didn't have to do direct substitution for this part of it, but you did for this. All right, if it's a property, you don't need to explain it, you don't need to justify it, you can just plug it in.
Basically, if you get tangent, you have to use both sine and cosine.
Mm-hmm. Yeah. All right, so some of these get a little bit challenging. You do need to think outside the box a little bit. Same exact thing with this one, number 15. Right? Again, I wouldn't just hand it to you. I wouldn't just tell you this is the property, use it. Right? What do you think we can do here? Okay, what can we factor? Okay, good. So this one's a difference of squares. So this one's cosine of x plus 1. And then cosine of x minus 1. Over, this is x times cosine of x plus 1. And then do we see that this cancels? So then we get the limit as x approaches 0 of cosine of x minus 1 over x. Is that a property? Yeah, if it's a property, you don't need to do direct substitution. You can just say that it's a property and I'll believe you. Right? This equals 0. All right, but that's all for today.